So some of the things that we want to keep in mind for safety. So when we do the radiophone, the students must always be properly dressed so that they're protected against the hazards in soldering. So soldering is a process where you're melting metal and you're going to be heating up the iron to typically over 600 degrees Fahrenheit. So your oven is like 450 for an hour or for 20 minutes to like cook some fish. This is 650, so way hotter than your oven. So you want to make sure that you're properly dressed so that, like, in case there's a small accident, you minimize the harm from it. So some of the things to be mindful of, we want to wear a shirt, long pants, or skirt, socks, covered shoes, and also safety goggles. Safety goggles are one of the things that some students want to avoid because they say that they're wearing glasses. You should still insist that they wear the safety goggles over the glasses. The glasses are not going to protect all the way around like the safety goggles do in case there's a splash of metal through the process. So while soldering itself is not generally hazardous, you typically have very high temperatures. This says 350 Fahrenheit. This probably should say Celsius because we're going to actually be soldering at 350 Celsius, so 650 or 662 Fahrenheit. You have to make sure your stand is properly supporting the iron. When you insert the iron into the holder, you have to make sure it's on a nice flat surface and that the iron is all the way in. If it's at an angle, this particular model won't fall, like it won't accidentally tip over, but some models it can fall out. So you want to make sure that the soldering iron is properly in its holder. Solder can drip. So depending on how you solder, when you're first starting off, you may not be doing a really good technique, and so you may be melting the metal and it forms a hot ball, and that can drip. So you want to be careful about not holding the soldering iron over your body. So you're going to be sitting down and you're going to be soldering, not having it over the having it over the workspace at all times. The other thing is that it generates fumes. So when you're soldering, there's something called rosin that's inside the solder, and so as it melts, it basically produces smoke. You don't want to be breathing that stuff in. So my general rule of thumb is that when I'm soldering and I'm melting, I tend to exhale rather than inhale. So just be mindful that it's going to be producing small amounts of fumes. You generally don't want to be working very, very close because that's how you can end up breathing in more fumes. The other thing is after you're done soldering, you always want to wash your hands. Generally, for what we're doing, we're going to use lead-free solder, and so it's less of a hazard, but it's good practice to always wash your hands. All right, so those are the main safety items that we'll talk about for soldering. Now I want to jump into the actual process of soldering. So I'm still going to keep with slides. Okay. Jump to here. Okay, so as I mentioned, soldering is the process of joining two metals. Now, this picture is very important because it talks about the proper technique to solder. So imagine that we have an object where we want to attach it to our printed circuit board. So soldering is the process of permanently attaching it. We want to push the object as close as possible to the board so that these leads aren't wobbly and possibly shorting into other stuff. The leads are going to go through the circuit board, and we want to attach the metal of the leads to the copper that's in the trace. A lot of people, when they're first soldering, they try to melt the solder and try to sort of drip it onto the connection. And that's a very poor technique. We want to always heat the joint between the copper and the lead. In order for the solder to melt and properly form a good electrically solid and mechanically robust joint, what we need is the copper trace and the lead to be hot so that both objects are what's melting the solder rather than the iron itself. In general, when you're soldering, you're not going to ever touch the solder wire to the tip of the iron. Now, there are going to be steps where we're going to clean and tin the iron, and in those steps, that's when you'll touch them directly. But when you're making a connection, you want to heat the contact area between the copper and the lead that's going through. Important in this process is the amount of contact area that the iron makes with these two pieces of metal. The contact area is going to determine how much heat transfers, and it's the transfer of heat, not the temperature, that's important for melting the solder. Now, it has to be, of course, above the melting point of the solder, but if you don't have very much heat transfer, you're not going to be able to melt the solder wire. So typically, you'll have a tip that's either pointed, or the ones that we're going to have for the STEM clubs, it has a chiseled tip. So the chiseled tip has a flat side, and it also has a region that looks much like this shape. And so we want to make contact such that we have some of this flat chisel end on the copper, so we get good heat transfer, and some of the tip touching the actual lead that's passing through. And then on the opposite side is where we're going to feed the solder wire. And the solder wire, because the copper and the lead are heated, is what's going to melt the solder, and it's going to form a liquefied region. And we're essentially actually going to form an alloy between the solder wire and these two metals. So it's important that these metals are properly heated so that so we're going to use something called SAC305. So S is for tin, SN. A is for silver, AG. C is for copper, CU. So it's 96% tin, like 0.5% of silver, and about 3% copper. So it's a lead-free solder. Typically in industry, they would use leaded solders, typically something like 63% lead, I'm forgetting it, 63% tin, 37% lead. So something of that ratio, but we're using lead-free. So we want to push this lead-free solder, and we want to heat up this joint such that we form an alloy that mixes the metals that are in the solder with the copper and with the leads. So after you've made this soldering connection, you want to inspect it. So very important that you form this good joint. So the good joint, the solder is equally, or it's uniformly covering the region of the copper, and it's properly connecting to the wire. One of the examples of the bad joint, you can see that there's this gap between the wire and the copper. So it's not really contacting the copper. If I were to push and pull this element, it's going to wiggle out. It's going to be loose. So you need a mechanically solid. So this one may be electrically connected, but it's not mechanically connected. In this case, this one has heated the copper, but not the wire, and so it hasn't formed the alloy between the solder and the wire itself. Okay, so some soldering tips. First, use adequate ventilation. You don't want to be working in a region that's very closed and confined because, as we mentioned, it's going to be generating fumes. So you don't want to breathe in these fluxes, and you generally want to work in an adequately ventilated room. So if you have room air conditioning, that's good enough. If you have a door that's openable, go ahead and open that. It's not a huge amount of smoke that's being generated. Holding the soldering iron. You want to hold the soldering iron how you want to hold a pencil. So you're going to hold it as think of it as just a really big pencil. I've seen a lot of students try to solder holding it like this, like they're about to stab something. They're holding it like a knife. You want to hold it just like you would hold a pencil. Just imagine that you're going to write with this object. All right, so heat sinks are a way that you can move some of the heat away from the board and dissipate the heat somewhere else. So typically, resistors are not a problem to solder. And the temperatures that you work with, certain types of components are very sensitive to overheating. So integrated circuits, the ones that are these black chips that have pins on them, you have to be very careful soldering. And in fact, most people will recommend to not solder those directly and instead solder what's called a socket header, which is basically just a plastic thing that you can then plug your object into after you've soldered. So the heat sinks are important for making sure that you don't overheat a component. So I'm going to also jump into the point of the temperature of the soldering iron. Typically, the soldering iron factory installed will come at 750 degrees Fahrenheit or 400 degrees Celsius. It's designed for a professional who knows how to solder. And it's designed basically when you're soldering, you're going to be putting the soldering iron in contact with this object for about 2 seconds. So you're going to go 1, 2, melt, 3, and you're done. Your students are not going to be able to be that skilled. What happens if you put the soldering iron at that temperature on this copper for too long? So I tested this out. It's about 6 seconds. It starts to delaminate. You actually start smoking the glue that's holding the copper to the board. And that's going to delaminate the copper from your trace. It's going to completely ruin your printed circuit board. So what we're going to do, we're going to teach you how to set the default temperature so that it's at 350 C rather than at 400 C. So your students can then hold this here for like 10, 15 seconds and not delaminate the copper. So one of the biggest failure mechanisms, so that plus having these bad joints, those are sort of the two biggest failure mechanisms that I've seen with novice people who are soldering. Okay, so the heat sinks, we're going to clip on. That's going to hold the IC. So let's say that this was one of the IC components. I would clip it to the IC. That's going to hold this in place while I do my soldering, but it's also going to dissipate heat so that I only heat this part, because heat's going to transfer along these leads. And so I don't want my object, my circuit element, to heat up too much. So I want to clip and remove heat from my very sensitive components and only worry about the leads. For the STEM Club activities, you generally are not going to be soldering anything that's sensitive. So this is not that critical, but when you get better at it and you do more complicated projects, it'll become important. Okay, minimize the time in contact. So as I mentioned, professionals, 3 seconds. That's how long it takes to make a solder connection. So damage to components is both temperature and duration. So we're going to solve the issue by reducing the temperature and allowing however long of a duration. Experts are going to do high temperature and they're going to do very short duration. You can also, for example, melt the insulation in wires if you solder for too long. Keeping the iron tip clean. So when you solder, if you start getting debris on your soldering iron and you try to make soldering connections, what's going to happen is you're going to get poor quality soldering connections, because in addition to the metal that you want to have alloying, you'll have a bunch of junk that's going to mess up your electrical conductivity. It's also going to mess up your mechanical conductivity. So you want to keep the iron clean. And the way to do this is that, and also you're going to, so if your soldering iron itself gets dirty, it's not going to be able to transfer heat as well as a clean soldering iron. So you'll be at a certain temperature and you'll expect things to melt and they won't melt. And actually, this is one of the other ways that you can sort of damage the soldering iron, not cleaning the soldering iron at the end of the day and just letting debris accumulate. It can oxidize the tip. And so once the tip gets oxidized, there are processes to clean it. It's really smelly, hazardous stuff to do. I'm not sure whether we're going to distribute that to the STEM clubs to do or not. But basically, you want to minimize the amount of cleaning that you have to do. You want to be able to have clean tips so that you get good heat transfer. So the way that you do the cleaning, the soldering iron will have a sponge. So you want to wet the sponge so that you can clean off while this is on. So the sponge will be wet, and you'll be soldering. You'll make like 1 or 2 connections, and the sponge is wet. You're going to wipe the tip off to get rid of that debris. And you're going to check the tip to see is it shiny. If it's shiny, then you're ready to solder again. The other part of cleaning that exists in these soldering irons is this brass. It's kind of like steel wool, but it's made of brass. This is used to clean at the beginning of the day and at the end of the day. We'll talk a little bit about the procedure for it, but just briefly, at the beginning of the day, you're going to take your solder. The iron will be on, and you'll heat up and you'll melt the solder on the tip. So you'll get a ball, a small-sized ball of solder. You'll let it sit for about 30, 45 seconds, and that's what's going to do. That's going to do something called tinning the tip. So you want the tip to be pretty much covered with tin. So you let that sit for about 30 seconds, and then this cleaning, which is the brass, you're going to basically stab the brass, and that's going to remove the debris, and then you'll wipe it on your wet sponge, and you'll inspect that it's clean to start off with. And so you want to do that at the beginning, and then at the end of the day to make sure that your tips are clean. Okay, so I mentioned heating the joint, not the solder, so you don't want to heat the solder itself, you want to heat the joint. Increasing the contact area of the tip and the joint. So in order for us to do this melting, we have to think carefully about if I make contact like this versus if I make contact like this, I'll have a different contact area. I'll have a different amount of heat transfer. So I want to increase the contact area of the tip. A lot of times students, when they're learning, they only have a very small, tiny portion of the tip in contact with the joint, and that tends to not be enough heat. So encourage them to come in at a flatter angle so that they make a larger contact area at the joint. After you're done soldering, check the joints. You want to check them visually, see that you have things that look like this good joint, where you have solder completely surrounding the wire itself. So you want to visually inspect it. It should look clean and somewhat shiny. If you have something that's very dull, or if it looks very rough, then it's generally a bad soldering joint. So another way to check is a mechanical check. If I push very gently on it, does the wire move? If it moves, then it's a bad connection. So I want to gently pull, gently push. In theory, I should be able to pull very hard and push very hard and it not move. So I want to double check that these are good joints.
I'm sorry, how long do you say it takes to cool? Is it like about 20 seconds or something?
About 2 or 3 seconds. It cools very quickly. So but it depends on the part. So if I were soldering something that has a lot of thermal mass to it, so I heat the joints, I heat the joints about 3 seconds. So as a beginner, it might be like 4 or 5 seconds. As an expert, about 2 or 3 seconds to melt the solder. And then after I've removed the soldering iron, it'll take about 3 or 4 seconds to cool off to the touch. Now, if I'm soldering something that's very large, that has a lot of metal, it'll retain that heat for a lot longer. So allow the object to cool maybe 20 or 30 seconds. It really depends on how much mass there is as to how long it takes.
Yeah, I was going to say also you can check when you're putting it together, it should be smooth and not like these little, somehow they have these little balls and it's like bubbly. You're like, that is not soldering. It should be smooth, almost like this versus a big ball like that.
I thought you said you wanted the cone shape.
No.
So you want this top shape for the solder. So sometimes what happens is sort of, actually they don't show one of the really bad ones, but a lot of times you get this huge ball here and this glump, and it's too much and it's actually not making contact with the bottom copper. So you want it to cover the hole, and you also want it to cover the wire all the way around. Sometimes people will make something that looks like this if you view it at some of the angles, but it looks like this when you view it at other angles. So you want it to look continuously connected, wrapped around the wire.
In what instance in the book you would refer to it as looking more like a cone? If you
cone.
Get it correctly.
Yeah, so cone being this shape rotated all the way around. Yeah, some other tips that I didn't fully mention. So you'll notice that when you put the object through, the lead is at a slight angle. And that's so that this object doesn't fall out while you're soldering. We typically use what are known as helping hands. So these helping hands, they'll have a magnifying glass. They'll also have these clips, and the clips are used to hold the board. Okay, so I'm going to pull out one of these boards. Suppose that I am soldering, and this is going to be what you work on this afternoon. So we'll have a circuit board that is pre-printed. So we ordered these circuit boards through an external vendor, and they've already surface mounted many of the components. We didn't have them do everything because there are certain parts that are very fragile, and then they also take up a lot more space. So this circuit board, what you'll be doing is you're going to be soldering these pins, these tiny 5-pin connectors, to this board. So this is a multi-step holding process where what you want to do, so you first insert the element into the board, and then you're going to want to clip it to hold it in place. So this particular one is already held in place, but I'm going to clip with my heat sink. So a typical object that I'm going to solder, I'm going to clip with my heat sink my actual component. So now that I've clipped this, my component is in place. But I also want to be able to hold the board so that I can work and solder. So some people, when they do it, they try to use the clip to both clip the component and clip the board while at the same time. I'm going to recommend that you have one clip for the component and a second clip that's used to hold the board. Now, often you will clip in multiple locations, so you can rotate these and basically hold the object in 2 spots so that this is a stable working space. And you can use your magnifying glass and bring it at certain angles so that you can see sort of what's going on in the circuit board. Bless you. I personally don't use the magnifying glass. I can generally see what's going on. But if you're doing really fine like surface mount work, that's when you definitely want to use the magnifying glass. Okay, let me finish talking about this stuff, and then I'll turn on the document cam to go over some other things. Okay, so the last couple of things, solder small components first. So generally when you're working, you want to put the smallest objects in first because it's difficult to get through and get like your soldering iron at fine angles to get to those small components. So you generally want to do the smallest components first. You can solder on small things like resistors, jumper wires, diodes, or other small parts before you do the larger things, which are typically things like capacitors or transistors. And you always want to install your most sensitive components last. So if I were to put my integrated circuit in first and heat it up and solder in place, and then I go to a lot of other soldering, there's a high chance that, one, I could overheat my sensitive component by doing soldering work near to it. 2, if I'm not careful, I can have electrostatic discharge. So as you get better at soldering and you do more complicated stuff, you have to and you're working with more sensitive components, you have to work with grounding straps so that you don't give your static electricity to these parts because they can easily get damaged. There are specific clothing that you'll wear, and you'll have wrist straps that are connected with clips to minimize electrostatic discharge. Okay, so I have my soldering safety goggles on. I got my long pants, and the first step is we want to wet the sponge. So just apply water to, I probably shouldn't do it over the document camera. Apply enough water that the sponge is damp but not soaking wet. So I have my solder sponge that I insert in. The brass can come out, so you can pull in and put out the brass. Generally, at the end of the day or so forth, maybe several weeks, you can shake out any loose solder that you've stored inside here. And this goes inside the front to be able to have an accessible brass cleaning spot. So generally for cleaning, the first cleaning spot is the sponge, and you only really use the brass, I don't know, first of the day, end of the day, or if there's something that just can't come off just by wetting it. So I'll do the first set of things with the soldering iron off. So the stand, as I mentioned, there's holders, and it'll hold it in place. You generally don't want to heat up the holders. It can handle it for a little bit, but not too long. So just be mindful that when you have the soldering iron in, it's securely in. This particular model, you can have it tilting and it won't fall out, but generally good practice, have it all the way in. The soldering base station is separate. So we have a base station and we have the soldering iron itself. So the base station has the electronics in it that are going to control the temperature. This particular model I've found, so this is a Hakko FX888D, I think is the model number. Very highly rated, so a lot of consumers have rated it 5 stars, but they've all complained that the user interface is very non-intuitive. Most people are used to a dial that just you turn the dial and it increases the temperature. This has 2 buttons, and you have to be careful about which button you push and for how long, because if you press the wrong button, you go into calibration mode and you screw up the calibration for your soldering iron. So the recommendation is that either we will or you will follow the manual to set the temperature to 662 Fahrenheit, which is 350 Celsius. And once it's set, when your students use it, tell them not to change the temperature or push any of the buttons. Power switch is at the side, and the soldering has a plug, so it's going to plug the main unit into the soldering iron. So this is the starting point for the soldering iron. So now let's talk about the circuit that we're going to solder. So as I mentioned, we purchased these circuit boards that have switches, they have a regulator, they have places for us to solder, they have surface mount LEDs, they have surface mount resistors. The reason we did this is to not have too many parts floating around. This takes care of a lot of the components that you'll need to be able to build the LED calculator. In addition, we can also get these mass-produced for relatively cheap, and actually cheaper than it would cost to get the individual parts and have your students solder it themselves. So this portion of the board has pretty much been done for you, but there are certain pins that need to be soldered in, and there's also the battery clip that needs to be attached. So what I've done so far is I've clipped what these are called Berg pins. I've clipped a row of 5 Berg pins into these 5 connections, and I want to solder all 5 of these. I have my helping hands, which is holding the 2 ends of the boards. I'm going to demonstrate the soldering with it off, just so that you get a sense of how this is supposed to proceed. So I have my pins already coming through, and as I mentioned, I want to heat the joint. So I need to look carefully, used to having this on this side, I need to look carefully at the angle of my tip. So right now this is the flat side, and so if I did this can work. I have a lot of heat transfer to the surface, not a huge amount to the tip, but this is about what I want to do. So I want to have it at an angle where I have about the same amount of contact area touching the board as touching the lead, and I have the flat end up against the lead. So I'm going to do, and the order is very important. So you want to heat, I guess I need to change my angle. Let me move this back into the screen. Okay, so I want to heat the joint first. I want to bring the solder in on the other side second. I want to remove the solder while it's wet third, and then I want to remove the iron fourth. So heat the joint, melt the solder, remove the solder, remove the iron. If I heated and I melted and I removed the iron first, the solder will get stuck to that. So I'll try to pull and I'll possibly break something. So heat, melt, remove the heat. And when you're doing this professionally, you should be able to do that in 3 seconds. So it'll be something like, if I'm doing this really well, 1, 2, 3 type thing. Your students probably are going to go 1, 2, 3, 4, 5, 6. They'll push way too much solder, 7, 8, 9, 10, 11, 12, 13. Yeah. So get them to have good practice and have them think about the process and work with the soldering iron before it's on. So go through the same exercise that I just did, where you're doing and just seeing 1, 2, 3. Okay? What were the words using in heat? Oh, so yeah, so heat, melt, remove. Okay. Other things with soldering. So sometimes you make mistakes. So you've soldered something and it's not in the spot that you want. So you need to undo and rework. So to undo and rework, there are 2 separate techniques to do that. One of them is to use what's called a solder sucker, and the one that you're going to have in your kits is actually different than this one. It's a slightly different model. And then there's the copper braid. So the 2 methods are, if you're using the solder sucker, the version that you're going to have, the functionality is pretty much the same. It's a spring-loaded device that's going to suck. So it's going to release and it's going to pull this back, and there's going to be suction that comes out of this tip. So what you do is you first load the spring by pushing it. Now, if you've used it before, there's going to be a bunch of solder at this tip, and so this is just going to fall onto the table. So I load the spring. So now this is spring loaded. There's a button that you're going to push when you're ready to unsolder, and it's going to go suck up the solder. Now, in order for it to suck up the solder has to be hot and melted. So you'll load the spring, you'll heat, so when you're first doing this, you might need 2 people, but this can be done with a single person. So you're holding the solder sucker in one hand, you're holding the iron in the other hand, and you're going to melt 1, 2, and you're going to place this directly on top. So 1, 2, suck. And if you do it correctly, it'll suck up the solder into the solder sucker. You may have to do this 1 or 2 or 3 times to properly remove, but once you've removed enough, you can typically mechanically start pulling the object out of the incorrect joint and then doing the rework. So that's using the solder sucker. So that's my preferred method. The other method is to use a copper braid. Now the copper braid, the copper has very good thermal properties, and it's able to wick, so it's actually called a solder wick. It's able to wick the solder up. Now with this, you have to think ahead and realize what you're doing. So what you're going to be doing is you're going to be heating the joint, right? So I melt the solder. I'm going to put this copper wick. The solder is going to flow into the wick, and then I'm going to remove the wick and remove the iron. The key, or the challenge, is you have to somehow hold the wick, and the wick is made of copper, and the copper is going to get hot. You put the copper wick over the area that you're going to desolder, you heat it up, and that'll wick the solder into the copper, and now I can hold just the plastic rather than holding the copper itself. Okay, I think we're ready to turn on. So, or actually, let me do one more thing. So the manual that will come with your soldering iron, definitely read it and understand it fully. I haven't read it yet. I've read just enough to know how to set the temperature, but definitely read it to be able to set all the settings. In order for, okay, so yeah, so I mentioned already, it's very easy to throw off the calibration by pressing the wrong buttons. Let me turn on the system, and let me show you partially what I mean by this, but I'm not actually going to do it. And if you accidentally change the calibration and you need to reset everything, it's a very complicated process that a few people have figured out and posted instructions online. We will include links to that discussion. We haven't tried it yet as to whether that'll work or not. But okay, so we plug in the soldering iron. And we turn it on with the side switch. So I had preset this to 662. So when I first turn it on, it starts off at 40. It's going up to 180. Right now it's 230, 250, 270. This is in Fahrenheit. 300. This is sort of the temperature you'd cook a chicken. 375, 400. All right, so we're still at temperatures. We're still at temperatures we understand. Now we're at 500. Takes about 30 or 40 seconds for this to heat up. Generally, you should turn off the soldering iron when it's not going to be used for more than about 5 or 6 minutes. The life of the tip gets degraded by leaving it on just over time. So if you're not actively soldering, have the students turn it off. So it's already up to temperature 662. It takes about 20, 30 seconds to get to temperature. So just have them turn it back on when they're ready. Okay, so now we are ready to solder. So the very first step, so I've just turned on the soldering iron for today. The very first step is to make sure the tip is tinned. So I will look at the soldering iron under the camera. It's actually in pretty good shape already, but let's say that it wasn't in good shape. I would melt, so I'm not going to do it over the camera. I would melt a bit of solder at the tip, and you can see it's generating smoke. And so I will let this sit for about 30 or 40 seconds so that the tip is properly tinned. So you can put it back in the holder for about 30 or 40 seconds. So while that's going, the next step is going to be that we're going to clean the tip with the sponge. Okay, so let's say that that's adequate time. So we look at it, and you can see, okay, it's not the cleanest looking thing, but as I wipe it with the sponge, what's going to happen is I'm going to get stuff that's balling up, and if I look at it again, it's going to look a little bit cleaner. I may need to wipe a little bit, wipe a little bit more. Yeah, so this one is relatively clean, and Terry brought up a good point. You also use the brass for tinning. So I forgot that step because I'm not used to working with soldering iron that has the brass. Okay, so yeah, so use the brass for cleaning the tip, so for tinning, and then I may wipe it a few more times. Okay, so I've actually picked back up some of the junk that I just put down.
Can an old oxidized tip be sanded?
It can be, but that's not going to last very long. So there's something called tip cleaner. So it's a tin and ammonium phosphate mixture. As a chemistry teacher, you know that's going to smell really, really bad. If we ever need to do this, the suggestion will be that, so they're like $6 off of Amazon. So if you find a tip that just doesn't work, go ahead and buy that stuff, but do it in a chemistry hood. So have it in a fume hood while you're tinning or cleaning the tip with that. Okay, so our tip looks relatively clean now, and we're ready to solder. Okay, so this is flat. All right.
You see the liquid.
Yeah. Okay. So the suggestion is having the solder at a 90-degree angle, having this tip come in like this rather than like this. So again, this is because of contact area. So in this configuration, I have a bigger contact area with the solder compared to how I was doing it initially, which is small contact area. So now we want to investigate the quality of the solder joint. So we'll take this out and look at it. I guess we'll rotate it around. So you can see that the solder is, hopefully you can see it. Yeah, so you can see that the solder is covering the pad completely. It's going all the way around the pin, and it's properly sealing. I can take the clip off, so I can turn this at the side so you can see like that. I should be able to pull and not have this come out. So this is robust and mechanically sound. Now, if you're professionally soldering, there would be another step once you're done with everything, which is a cleaning process. So the resins and so forth and the solder, depending on the type of solder that you get, it'll say either no clean or rinse clean, or I forgot the third type is. But basically, depending on the type of solder that you use, you have to treat it with chemicals. So you do a spray so that you remove the harmful parts of the rosin from the soldering circuit, so that the part can last for a very long time. If I just left this how it is, depending on the type of solder that I have, the joint may fail over time. So now that I've done one, I'm tempted to do more. Let's improve my technique. So let's see a few more. So once you've done one, you can remove the heat sink from it. So we're going to do, and again, when you're soldering, you just have to be careful what's in the neighborhood. While I'm soldering this, I don't want to be melting the switch. So that one, yeah. I think also the solder itself might be cold. That's why it's taking longer to melt. But once I've done a couple, then they go much faster. It's like the first one to melt took a long time. So if you look at it carefully, what'll happen is if you do it quickly enough and you remove the heat correctly, the solder itself, okay, so the pins are still kind of warm. The solder itself won't bridge. The resin and the residue will bridge. That's insulating. So you can double check it with an ohm meter and measuring, or your digital multimeter, and measuring if you have circuit continuity. Yeah, the metal part adheres to the copper, but this resin stuff spreads out throughout. So what you'll do today, you'll be doing some practice ones, and then you'll do the actual chip that we're going to use later in the week. You're going to be putting in a set of 5 pins on one side and a set of 5 on the other. Now, I forgot to mention this, but the design of this chip is such that it'll plug into your protoboards. So we're doing a hybrid chip where we're doing some things that are permanent and some things that are temporary. And the reason that we're doing it this way is because there are certain parts of this that are very complex, and it's like a lot of jumper wires. And so we've abstracted that portion out of the project and kind of done that for the students. But then the important parts, understanding the logic gate connections, we wanted the students to be able to do. So they'll do that. And so the other thing is that this board is slightly unusual in the sense that we're going to make all our solder connections on the top. So normally in a typical circuit board, you'll have your components on the top and you'll make your soldering connections on the back side. This particular board, it has surface mount components, which make sense to surface mount on the top. Through-hole components would make sense to solder on the back, but the way that we're going to use this is we're going to plug this into a proto board. So we can't have solder connections on the back side because then that won't go into the proto board properly. So what you'll do is you'll insert these pins through the back side of the board, so the short part of the pin through the back side of the board so that it goes all the way through. You make 5 connections on the bottom, 5 connections on the top, and then this portion of the circuit is done. The second portion is to attach the power supply. So the power supply will be a 9-volt battery clip. And what we've found over time is that if you just solder this directly to it, it can get pulled out. So to minimize that, we've put holes near to it. So we're going to solder to the top. So what that means is we want to feed these wires through from the top.
Can you push it through the camera? We don't see it.
Oh, move this over. Yeah. So you want to push the wires through the top 2 holes, have them go through the back side, and then have the back side come back through the front. Yeah, it's not staying. Okay, so I typically would do these one at a time. Maybe I can do 2 at a time. We'll see. So now they're up at the top so that we can solder. So you can press them so that they sit flat. And so we want to solder them like this so that in case someone pulls this, it doesn't come out.
Go back to the camera.
Oh. Okay. So what I did is I have the wires going from the top through the back and then coming back out through the front. And then this now I can solder at the top. So all my soldering connections will be at the top. Okay.
12 solder connections.
So 12 soldering connections overall. And you saw that the very first one takes a long time, and then once you get the hang of it, you go boom, 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 boom. It's all done. So let's say that this is the end of my day. I'm going to clean off my soldering iron. So I'm going to wipe it with the sponge, a few stabs with the brass. I'm going to look at it to see, does it look smooth and clean? This one seems like it still has some loose metal on it, so I'll wipe it a little bit more. A few more stabs of the brass. Okay, so it's back shiny again all the way around. And now I can turn off my soldering iron. Before I turn it off, I wanted to talk a little bit about the buttons on the front and how people get confused. So in order to change the temperature, what you do is you press twice, or sorry, you press and hold. Where did it go? Changing set temperature. Yeah, so you press and hold the enter button for 2 seconds. So once I've pressed and held the enter button for 2 seconds, now the first digit is changing. So the 6 is flashing. So I can go up 700, 800, 900, then it restarts 1, 2, 3, 4, 5, 6. And then once I'm satisfied with the first digit, I press enter, and then I go up again and I set the second digit. Press enter again, I set the third digit. Once I'm satisfied with everything, I think that's it. I press enter again, and this is now the set temperature. If you accidentally press up for 2 seconds rather than enter for 2 seconds, you go into calibration mode. And so the procedure looks like if you're setting the temperature, but you're actually changing the calibration of the system. So that's why a lot of people complain that it's very non-intuitive to use, and so don't have your students changing the temperature. All right, so we're done with this. I'll turn this off. The soldering irons that you're going to use in the other lab, they're a different model, so a different manufacturer, different model. Those are the ones that are used in the labs. I would say that every soldering iron brand and model has its advantages and disadvantages. Those do not have a digital set temperature. Those are going to default to the 400 degrees. So when you solder, just be careful that you're not heating for way too long that you're going to delaminate. I think it's slightly less than 400 that those are set to. Some of the other things to mention, the soldering iron, again, the reason that we picked 662 is as you go higher, like once you get above about 700, it wears out the tip much faster. So keeping it at a low temperature preserves the life of the tip. The schools will be provided with 3 soldering irons, 3 replacement sponges because the sponges get beaten up, especially if students forget to wet them, and then 3 replacement tips. And so in case your tip gets in such a bad shape that even if you try the tin and it doesn't clean off the oxidation, you can just replace the tip with a fresh one. The tips are about $5. The soldering iron's about $85. So, and then the sponges are like $4 or so. So it's parts that should last for years. The soldering iron I have in my lab has lasted 12 years. And so if you take care of your equipment, it'll do good.